Hi class, we are starting chapter 9. Chapter 9 is all about numerical methods, numerical solutions to differential equations. We saw we saw one numerical method in chapter 2.6, which was Euler's method. So we're going to talk about some other methods throughout this section. At this point in time, I'm not making all of the videos for chapter 9. Possibly in the future I will make the rest of the videos, but for right now we're only going to go through 9.3. So again, maybe you're watching this later in the future and I have all of the chapter 9 videos made. Okay, so again, in chapter 2.6 we saw how to approximate the solution curve to a differential equation given an initial value by using Euler's method. Okay, so at this point in time, if you want to pause or go back or look through the textbook for chapter 2.6 for Euler's method, it would be nice to have a review for that, right? So when we use Euler's method, we have some equation, our differential equation. Most of the time it's not solvable, right? So for all the examples we have here, we'll use the exact same example that we did in chapter 2.6, and we're going to expand on that example. It's a nice example because we can actually solve it and find the solution, and then talk about the errors that come up from our exact value versus our approximations that we're going to come up with, right? So a lot of times we can't find the solution, which is why we use an approximation method, a numerical method in the first place, right? So generally what's given is an initial point to start us off and our equation, and we use those two things to kind of get started, right? So it's basically an initial condition and an equation. So for our example in chapter 2.6, again, we were able to actually solve for the exact solution, which allowed us to analyze the error in our approximation because we can compare the exact value with the approximate values, right? We found that our error decreases when we decrease our step size, right? So if from x1 to x2 is rather large, right? If we decrease the size from x1 to x2, then our approximation will be better, right? So for instance, if x1 is 1 and x2 is 2, there's a large error that can come up from there, right? If x1 is 1 and let's say we half it and we use x2 as 1.5, there's going to be a lot less error than if we use the value 2 for x2, right? The point that we're interested in looking at. The smaller h is, the better our approximation. However, the problem with that is that the smaller we make h, the more computations we have to make, right? So if I have a very small value for h, a small step size, I can be fairly accurate for the, compared to the actual solution, the actual value. However, it can take me many calculations, many iterations of the algorithm before I reach the required approximation that I wanted to get to, right? So the step size kind of dictates how much work I want to do, right? So ideally I could do the least amount of steps and be as accurate as possible. That would be great, right? There's other forms of error. Okay, so at this point we're going to talk about round-off error. Okay, round-off error comes from rounding off values, right? Either manually, right? I'm going to cut off all my digits after the 4th decimal point. I'm definitely going to have some error, right? Not only that, but when I do my calculations, my computer or my calculator, whatever it is that I'm using, also only stores a certain number of digits. Okay, so for instance, if you use floating point or if there's a cap on the number of digits, you're only accurate to possibly to as many digits as you are using, right? So I think a standard computer will use it really depends, right? You can use 32 digits, you can use 64 digits, right? 32 and 42-bit. So the number of digits of calculation will also determine how accurate your approximation is, okay? So let's go ahead and do an example, okay? So let's say that I have this as the equation or the function that I'm interested in. X squared minus 1/9 over x minus 1/3. Okay. If my value of x that I want to plug into my function, equation, expression, what I have you is 0.334, okay, a 4-digit value, okay, so this does not necessarily mean it's an approximation, this is just the value that I'm using, right? So let's say that the fractions that are already present, I use 4-digit approximations for, right? So for 1/9, I use the approximation 0.111, and for 1/3, I use the approximation 0.3333. Okay, so when I plug these in with my x value here, right, so I have my decimal approximation. So 1/9, if you plug it in your calculator, just has 1s forever. 1/3 is 3s forever. So obviously sooner or later, if I'm going to plug them in and do calculations with them, I have to stop somewhere, right? I can't just plug in 1s forever and 3s forever, because then I'll never actually press enter, right? So let's say we cut them off at 4. So plugging in these values here, right? So I have my x value and my decimal approximations. I get out the value 1, okay? Now, if I use the exact values, the actual fraction 1/9 and the actual value 1/3, right? So exact means exact, right? Decimals are approximations. And I still have this value 0.334, okay? I get basically 2/3, right? I'm rounding this to the 4th decimal place because that's what I've been using so far. So if I round this to the 4th decimal place for my answer, obviously I'm going to get out 2/3 here, or 0.6666666 forever. So how does me basically taking something that I'm not even rounding up or rounding down and just cutting them off, truncating the error at that point, right? Truncating the values, I'm just chopping them off and not needing to round. I have a significant difference in my output values, okay? And this is only to 4 decimals approximation. Imagine if I use 0.01 and 0.03 and try to do the same thing, okay? So that's a 33% error, right? A third, from 1 to basically 2/3, okay? That's a lot missing. So imagine if I did that with your grades, for instance, okay? If you went from 100% to basically a D, right? Or vice versa. So using the exact, and you get one value, and truncating your values, you get a completely different value. So your grades are not reflective of the actual work, right? So imagine that every single time I do my calculation in my algorithm, I'm now compounding this 33% error, right? So again, imagine that this was the first calculation and I had to do this, use this output value and do more calculations with it. Not only do I have an error, or I'm sorry, let's say that this is my value because this is where the error is, and I start using this in my calculations, I'm taking the error that I have and I'm increasing it, right? Every time I have to do it in an iteration of my algorithm. So it's very important that we try to use as many decimal points as possible. When I do your calculations for these videos, I am using as many values as I possibly can, even if I only show you 4 digits of the actual output. When I'm doing the calculations or using those, even those previous outputs, those previous 4 digits, I'm using 20 of those digits, even if I'm only showing you 4, right? So to be as accurate as possible, you want to use as many of the values that was given to you by your calculator or computer or what have you as possible, even if you only show so many of those digits, okay? So let's come back to Euler's method. So let's think about what this method is when we're talking about errors, right? I am most likely looking at a solution curve, okay? The solution to my differential equation is probably a curve. So remember, we always have e to the some power in our solution, or it's sines and cosines. Those are the general things that make up our solutions, right? When we look at first order and the higher order values, right? Systems of equations, they all have sines, cosines, e to the alpha x, right? What have you. Those are all curves. Euler's method uses a straight line from one point to another point to approximate a curve. you will never get the exact same value as a curve if you are using a straight line over and over and over again, right? The best you can do is to try to choose a new point from your previous point to draw the line through those 2 points, right? That's what you need for a line, is 2 points, so that you can approximate the curve as closely as possible, right? So there's an inherited error in trying to approximate a curve with a straight line, right? Which is what we're doing. So in each iteration of our algorithm that we're applying with Euler's method, our error increases, one, from the truncations, right? From the values that are being cut off, that are no longer stored either by us on accident or by our calculator or computer. And we have an error that is compounding, one from the calculation itself also, and also because we are trying to approximate a curve with a straight line. So there's kind of three things working against us at that point, right? So the error from one calculation of the algorithm to the next, right? So basically from yn to yn plus 1, that's called local truncation error. So that's the error that happens from one approximation to the next approximation in the algorithm. Okay, so if, for instance, if I have to run my iteration 6 times, there's 6 local truncation errors that all build up and add together. Another term for this is formula error or discretization error. But if I add up all of those local truncation errors, that's going to basically give me the global truncation error. So the global truncation error is the total error over the entire algorithm, right? So my actual value for the value I'm trying to approximate. Okay, so if I'm trying to approximate y of 1 and my actual value of y of 1, right? So the difference between the actual value and my final approximation, that's the global truncation error, right? So if we assume that yn is correct, then yn plus 1 will contain a local truncation error, right? So from one step to the next is the local truncation error, and over the entire algorithm is the global truncation error. Okay. If the solution y of x, right, so the actual solution to the DE, okay, has k plus 1 derivatives, then its kth degree Taylor expansion centered at x equals a on an interval containing a and x, so the interval of existence has to contain a and some values around it, okay? We're looking at the Taylor expansion up to the kth degree, right? So up to the kth degree, so the kth Taylor expansion. So what that looks like is y of x is, so I think I'll put equals, but it will basically be an approximation, right? A Taylor expansion is an approximation. So I'm going to be plugging in a, so y of a plus y prime at a times x minus a, because I'm centered at x minus a. And remember, this degree just keeps on increasing. Here, the degree of this term is 1. Here, that term is a degree of 0. That's why it's not present. The next one would be y double prime, 1/2 y double prime evaluated at a times x minus a double prime, squared, okay? And so forth and so forth and so forth, right? I don't have a lot of room, so I didn't write everything, but you guys should be familiar with Taylor expansions because you are past calculus 2 at this point, right? So the general form of each term looks like this, right? So at term 0, this is 1 over 0, right? 0 factorial, so that's just 1. Y to the 0th derivative, so just y, evaluate at a, x minus a to the 0 power, so that's y at a. The first term here, so that's 1, y first prime, evaluate at a, x minus a to the first power. The next one is 1 over 2 factorial, y to the second derivative, evaluate at a, x minus a squared, so forth until again we get to the kth term, right? The kth degree term. If we look at the very next term, okay, that is our remainder. This is the term that we look at when we're trying to look at the error, right? The maximum error possible. And we'll talk about that in quite a bit. But this k plus 1th, this next term derivative, the next degree higher, is a remainder term. It is very, very small, okay? This is large, this value is smaller, the next one is even smaller, and the next one is smaller. We're adding smaller and smaller and smaller values, smaller and smaller corrections to approximate our curve, right? If you think about what a Taylor curve is. The very first term is really just a straight line approximation. The next one gives us a quadratic approximation to whatever this is. The next one gives us a cubic approximation, and so forth and so forth and so forth, right? So this next term adds very, very little information and is considered a remainder, and is how I'll look at the maximum error possible. So I'm preferencing this now, right? Just so that you know where things come from later, okay? So notice here that we're not evaluating at A, right? We're evaluating at some value C. We do not know what C is, but we do know that C is in between A and X, meaning it's on the interval of existence. Okay, so let's assume that we let k equal 1. Okay, we'll talk about why we're using this value later. For right now, just roll with it. Okay, A we're gonna say is x sub n, or the current value that we're at or that we're interested in, right? So we're gonna say that x is the next term, right? A is the current term, x is the next term. So another way of talking about what our next term is by looking at the term that we're at and adding h, our step size, right? That's how we get to the next term of interest. So if we plug all that into our Taylor expansion, we're going to have y, again, x is now xn plus 1, okay? Y of a means I really have y of xn plus, so again, k is just 1, so we're only going up to this value. Okay, this is k is 0, this is k is 1. So we're only going to look at these first two. Okay, so y xn, this will be plus y prime xn, xn plus 1 minus xn. Okay, we make those substitutions. So here, if I add in this k plus 1 term, right, this is going to be the last part that we have, right? Because this is k plus 1, so k is 1. We're entering at 1 extra. So this is my remainder. Okay, and again, that's how I'll be looking at my approximations, my errors. And that should make sense because look at what this is, right? This is just Euler's method, right? So if you watch 2.6, you should see that. So this is Euler's method plus some extra little bit, which is our remainder, right? Which we use to calculate the error. So we'll have our yx sub n plus our y prime x sub n. If this is the next term and this is the previous term, the difference between these two is my step size. Okay, same thing here. The difference here is my step size, so this is just h, right? So I get h squared and this is h. Okay, so again, previous value plus a step size times y prime at my evaluated at my value, right? Oops. Okay, so my new term is this previous value plus h times my y prime evaluated at my current value. Remember, y prime is equal to some function. Okay, so this whole thing is my next term. So my next term, my next approximation, plus an error term. Okay, my local truncation error. Again, C is somewhere between my current value and my next value, right? So a distance of h is where C lies away from my current value. So somewhere within a distance of h. Okay, C here, again, it's unknown. So we can compute here this local truncation error. Again, I don't know what C is, so this y double prime evaluated at C, I will call M. M So again, look, 1/2 h squared. So this is m. M is the max value of my second derivative evaluated in the interval between my current value and my next value. Again, C is somewhere between there. Okay, and that's what we're going to use to maximize the error possible, right? So big O, h to the nth power, is the notation for truncation error. This is called big O notation, right? If our local truncation error is big O h to the n, then the global truncation error is smaller than that. So it's big O h to the n minus 1 power, right? The global truncation error is smaller, so the error isn't smaller, but the bounds for the error is smaller. Okay, the values in the difference in values is a smaller value. Okay, so e to the h is the error function that defines the error in a numerical calculation based on h, our step size. Okay, this is not the constant e times our step size, right? E is an actual error function. So e to the h is said to be of order h to the n. So the absolute value of my error is less than or equal to some constant multiple of h raised to the power of n. Okay, and again, n is based on the error order, right? The big O notation. Okay, C is just some constant. H being sufficiently small, so again, these approximations don't work if I'm going from x equals 1 to x equals 10, right? I can't go over large intervals. My step sizes should be small in order to have good approximations. So the local truncation error for Euler's method is big O h squared, which should not be surprised because look at my local truncation error here. The h value is squared. I have second derivative, okay, included in my error calculation, right? So the local truncation error for Euler's is big O h squared. So that means that my global truncation error is n minus 1, so 2 minus 1 or 1, which should make sense because I have, again, here, just a first derivative, or h to the first power, right? In the next term, when I'm calculating the next term, I have h to the first power, first derivative, so my error here will be big O h1. The local truncation error, second derivative, h squared, will be big O h squared. Okay, so we got to look at either the derivative that you're using or the h value, right? So note that if we half the step size, so we cut h in half, then for Euler's method, we get our error bound here, right? So the bound for the error to be big C times 1/2 h squared, right? Which is the same thing as h being squared, 1/2 being squared, which is 1/2 squared, a 1/4 reduction of error. Okay, so it doesn't cut it down by 1/4, it is 1/4 of the value. That is a huge decrease. You can think about that as a 3/4 decrease or a 75% decrease in error. That's a lot of error being reduced just by cutting the step size in half. So let's go ahead and do our example. Okay, so we want to compare h equals 0.1 to h equals 0.05 for our example from chapter 2.6. Again, if you watch chapter 2.6 right before this video, things will probably make a lot more sense. Well, not that they won't make sense now, but they will make more sense. Again, this example we are going to use for the remainder of chapter 9, right? Or at least through 9.3. Okay, so it's a good example, and we'll continue to use it and compare our different methods against it. So the problem was y prime equals y plus xy. Starting point is 0, 1, and we're trying to get to an approximation value for y at 0.5. Okay, so in 2.6 we found the solution. We found a series of approximations, so we're really just going to sum that up here. We're not going to do the entire Euler's method again because we already did it in 2.6. We're going to summarize the values and compare our approximation for 0.1 to our approximation for 0.05. Now, completely honest with you, I don't remember if we did both in 2.6 or just the one. So regardless, we're going to have the values here. Okay. So here is my table of values. And again, just as a disclaimer, even though I'm only giving you 4 digits of accuracy, okay, I use a minimum of 11 digits of accuracy when I computed my computations. So I didn't just find this value and then use it to find this value. I have, to be honest, I have about 15 digits after this one in my computations. So for all of these values, these are accurate. I kept it accurate to 18 digits. Okay. For my absolute error and my relative error, I used 11 digits of accuracy. So I used the 18 digits here, but my actual values, I only had 11 digits of accuracy. So for the absolute value and the relative value, there's a little bit difference. Okay. But these are extremely error. The errors that pop up here are 18 values down, 15 values down, right? So these are very, very accurate. Of course, I rounded them off to the 4th digit, so there is some rounding going on in the display. However, in the calculations, I did no rounding at all. I used whatever it is that my calculator and my computer system gave me, okay? So again, when you calculate these things, stay as accurate as possible, okay? So for h equals 0.05, same thing. I have my table of values. Again, I am minimum 11 digits of accuracy, even though I'm only displaying 4 digits of accuracy for every value. Okay. So here you can see I used the complete values that I had possible. They're actually displayed at the end. So this value, even though it says the relative error is 0.0303, this is the actual value that I had computed, right? 0.3, here this was 8, so obviously I rounded to 3, but I have several digits, okay? This is the last value for 0.5 for our relative error, right? I have 0.0571. So take the 6, I would round it to 1, but here is all of the values. So when I'm looking at my complete difference here, right? So my h equals 0.5 versus my h equals 0.1. If you look, that's about half. Okay. So again, so look at our final answers. Okay. So let's just come back and look at just here. So this, okay, this is the input that I'm in, right? First I started at 0 and I'm going up by 0.1 for each of my x's. These are my approximation values. Okay. So at 0.1, this is my approximation. This is the actual value, right? Here's the absolute error, right? So again, absolute error is the difference between these two, and I'm just keeping the error positive, okay? So even if I get out a negative value, I'm just taking the positive value of the error. And then here, I'm taking, for relative error, I take the absolute error, and I divide it by my actual value, okay, to get to the relative error. So again, there's like 10 digits here, there's like 10 digits here, right? So I divided, there's actually 10 digits here, I'm only showing you 4. So let's look at our absolute error. So at 0.1, notice that the first value is 0 on all of these, and I have something in the hundredths place, right? Except for the last value. And notice also that it's increasing. 0.01, 0.02, 0.04, 0.07. My absolute error is increasing as I go through each iteration. Okay. My relative error, okay, generally this is a percentage, but I decided to just keep the actual value. So if I use this as a percent, my percentage relative error, move this to decimals, is 0.96%, right? So less than 1% relative error, right? Which is pretty good, okay? And as you notice, my relative error is growing as well because my absolute error is increasing, right? So here was my approximation for step size of 0.1, 1.7616 versus 1.8682. That's not too far off, right? But as you'll see later on in the other videos, we can get much, much better. Okay. So that is us looking at the first Euler method with a step size of 0.1, right? For the other one with a step size of 0.05, obviously I had to do twice as much work, okay? Here, I only had 5 calculations. This one doesn't count because this is my starting value, okay? Here I had to do 5 calculations. That's not too bad, but if you remember in chapter 2.6, doing this by hand is kind of a pain in the ass, right? So here, I have to do it twice as much, okay? So notice for my first value, my absolute error, it's a little bit better. It's actually twice as better, right? Because before I had 1 0 here, now I have 2 zeros. So instead of being accurate to the hundredths place, right, or semi-accurate to hundredths place, I'm accurate to somewhere in the thousandths place, right? Actually, to reverse that, I'm accurate in the tenths place here. Here I'm accurate to the hundredths place, right? So about that's pretty accurate, okay? Notice for my final approximation, I at least have an 8 in front. So that's pretty nice, right? The other one I didn't even get to the 8s. I only got to 1.76. Okay, I was about a tenth off, which you can see here, a tenth, right? Okay, here I'm off by half of a tenth, right? Which is pretty nice. So if I compare my errors, right, my final errors, my global truncation errors, right? So I'm looking at the very final example, and I'm taking the better one on top and the worst one on bottom. That's about half, okay? Which is pretty interesting, especially since my step size got cut in half, okay? And if we look at the way that our errors work, I cut it in half. But if I'm looking at the global truncation error, I'm not squaring it, right, like I did here to get a difference of 1/4. It should be just C 1/2 H. So I should get half of the error, which I do because I'm looking at that point at the global truncation error. Now, if I looked at the error from here to here, right, and the error from here to here, and I computed it, it should be about 0.25%, right? So that is a 25% reduction. So this just about halving the error by halving the step size globally at the very last step agrees with our global truncation error of Euler's method when we halve the step size, right? So for my big O notation, this is for global. So again, coming back here, remember for global, for Euler's, right, local is 0h squared. That means that the global is 1 less than that, or big O H, right? Right? So big O H means that if I take my error function and I take it and I throw it in half, that C to the 1/2 H is just that error cut in half, right? It cuts the global error in half, which is what we saw happen here, right? Just about, almost in half, a little bit less than half, right? About 47% basically, just about, right? So let's look at another example. We want to find a bound for the local truncation error at each step for Euler's method, okay? Not just the global, not just at the end, but at each step. I want a bound. What's the maximum error I have from one step to the next, okay? Here we're going to be using H 0.1. So we're going to be looking at when I'm lazy, when I don't want to do a lot of steps, right? What's the maximum error I can expect to have, okay? So we need to bound our error, right? So we're doing the local truncation error. So I'm using big O H squared, right? This is for global. For local, come back here. For local, we have local truncation error is big O H squared, okay? All right. So in order to do this, I need to find the second derivative of y, right? So when I say y, not this y, because this isn't y, this is y prime. I know what my actual solution is because, again, for my example, we were able to solve it using linear methods, okay? So, again, in 2.6, we went over the solution. So I'm just going to do it here. I'm not going to actually solve it. but we're going to take it and we're going to find its first and second derivatives, and we'll put a bound on the error by looking at the max value in between 0 to whatever other point. Okay, so we're actually going to look at this globally instead of just from one step to the next. So my solution was e to the x plus 1/2 x squared. Take its first derivative, right? So I take the derivative of this and it comes in front. That's my first derivative function. This is my second derivative function. Now let's look at what this thing is doing. This is a polynomial. This is an exponential. We are starting at 0 and we're moving towards 0.5. So this grows from 0 to 0.5 and this grows from 0 to 0.5. So the max this function can be over the entire interval from 0 to 0.5 is going to be at 0.5 because it's always growing along x. So if I really want to bound this completely, from one step to the next is fine. I can, if I'm interested from 0 to 0.1, then I would choose 0.1 and plug that in here, right? But the easier way to do this is to look over the entire interval and just plug in 0.5, and that'll give me a maximum error over the entire iteration locally, right? Not globally. So since y double prime of x is increasing, we choose the largest value in our interval for c. So from x naught to xn, again, x naught is 0, xn, my final iteration is 0.5, right? So I'm going to choose c to be 0.5. If there was a different maximum at some other point, maybe this function had a maximum right in the middle, right, at 0.25, then that's the value I would use. But it's not. It's very clear to see that this is increasing over the entire interval, right? So I'm going to plug in my stuff here. My m will be this evaluated at 0.5. Okay, so I have 1/2 h squared, and then my second derivative evaluated at 0.5. Okay, so 0.5 squared plus 2 times 0.5 plus 2 times e to 0.5 plus 1/2 times 0.5 squared. So that comes out to approximately 0.0303589968. So that means that from one step to the next, from 0 to 0.5 at any one of those iterations, my local error should not exceed this value. Okay, so let's look at this and see if that's true. Okay, right, and that's almost true, right? So that's over the entire thing. If I wanted to minimize that, then I would have chosen from 0 to 0.1 because that would have been the smaller error. But I'm choosing a largest error possible, right? So I wasn't finding a minimum error between any two values. From here to here, I wanted a bound, right? So what I found was a bound for my error. So from here to here, this is almost 3. Okay, it's almost 3 because this is a little more than 7, right? This is a little bit more. It is. It's more than that. So I can find the difference here, okay, and that will, it should be within my tolerance levels, right? So this is also very close to being within 3, okay, and not just 3, but 0.3589968. Okay. So if we were to do this for h equals 0.05, then this would be the bound at each step. Okay, it shouldn't exceed this much at each step. Right. So note also that if we take the ratio of those two bounds, okay, I get 0.24811236069. Okay, which should be, if you look at this, this is almost 25%, right? Which is close to our computed value of a 1/4 reduction factor in the local truncation error for Euler's method when halving the step size. Okay, oops. So here, right? That was back when we were talking about here. So we're looking at the local truncation error. What happens when I half the step size and I plugged it in? Well, we did some little math here, and we distribute the square, and we notice that this is still the error for the local truncation, but I get 1/4, right? So from not having it halved, right? If I were to just plug in h here, ch squared, and then halving that, so c 1/2 h squared, there's a difference of 1/4. Okay, so if I plug in 1/2 h, there's a 1/4 reduction in error, and that is what we got when we looked at the computed possible error as well. Okay, so again, everything here is decimals, everything is not exact, all of these things are approximations, but it helps us to put a bound on what we would expect to happen, right? So again, a 1/4 reduction factor means that we have 75% reduction in error. Okay. So now let's look at the improved Euler's formula. All right, so the improved Euler's formula is a predictor-corrector method. So we predict the value of y of x of n using Euler's formula, which is given here, right? So my next term is my current term plus a step size increase times my function evaluated at my current term. So here, notice that we have a star here because that is my corrector. This is not the actual value I'm going to use. I'm using this to predict what my value should be and then incorporate it into my next calculation. Okay, so we're going to use that predictor because that's predicting what my next value would have been under the standard Euler's formula. And I'm going to correct my estimate by doing Euler's method at that point. Okay, so basically what I'm doing is I'm doing Euler's at my current point, okay, and I'm doing Euler's at my next, what I would assume to be next point, and I'm finding the average of that and adding it to my current value, and that's my next value. Okay, so again, this is the next Euler's. Okay, this is my Euler, which I'm doing here, right? Same kind of value, right? It's still a HF at x and yn, and then I'm taking that value and I'm plugging it back into the formula to get what I would assume is the next formula, and I'm averaging those two values together and adding it to my current value. So starting with y prime equals f of xy, y is x naught equals y naught, and h, we would have y1 star equals y naught plus hf x naught y naught. Okay, so this would be my first approximated value. So I'm going to take that, right, this y star, the x star, x1 I already know because I'm just adding another h to x. So I'm going to take this output that I had and I'm going to plug it back into Euler's formula, okay? And I'm going to use that with not the entire value because that's what I just found here, but you know, the first part that I found by plugging my current point into my formula, my first derivative formula, and adding those two together and adding it to y naught, right? So we're basically again finding the slope based on what would be our next point and our current point, okay? So I'm using my current value, I'm doing what would be my next value, and I'm finding the slope between those 2 points, basically. Okay, that's basically what this thing is. Okay, plus the y-intercept at my point. Okay, taking the average and using that line to find our next point. So it looks like this. Okay, so I know there's a lot of stuff going on here, but this is x naught and x1. Okay, so normally what I would have is my x naught, y naught. This would be my next point. That's what we were doing before. I was finding my new point. I would draw a line between those two, and then I would find another new point, right? And then that would be my next line. So what I'm doing is I'm finding my next line, and I am somewhat finding the next line. Okay, so if you see here, that's my current output. This matches with what I would have if this was the next output, but it's not, right? So I'm using the output value of what would be the next step after the one that I'm actually on, and I'm averaging those two values together to get a new line from my current point to the actual point. Okay, so that's what's happening here. So as you can see, that's a much better average. Okay, a much better approximation there. So let's do an example. Hey, look at that. We're using the current one that we just did. Okay, so we're going to do it again with both points, h equals 0.1 and h equals 0.05. And we're going to compare the percent errors. So we're actually going to just do the relative errors. If we needed to turn those to percents, we can do that. Okay, so for h equals 0.1, my first point is 0. My first output is 1. Okay, my y1 star is just me plugging in 0, 1 to my function, right? So I have my current output plus my step size h times my equation, right? Y plus x times 1, right? So I'm just throwing it all together and I get an output of 1.1, which we already knew because we've seen that before, okay? So that is my y1 star. So now what I'm going to do is I'm going to plug in 0.1 and 1.1 into my formula, right? So my whole formula is going to be my current value, which is output of 1, plus my half of h, okay, times my current value, okay, so 1 plus xy, okay, plus, now I'm going to do that with my new point, 1 plus 1, so this is my y plus xy, right? So I'm plugging in my current value, 0, 1, and I'm plugging in what I would assume to be my next value, which is 0.1 and 1.1. So this is the first half plus the second half, right? Y plus xy, and then also y plus xy. So I'm adding those two together, and I'm taking its average. Both of those had to be multiplied times h. So I just pulled out the 1/2 and the h. Okay. So when I put those together, I get 1.1105. So if you remember from Euler's, when we're doing just h equals 0.1, I think we had 1.1107 or something like that. Let's come all the way back. Okay. I had 1.1107. And I had I had 1.1. Okay. 1.1 was my approximation. So I got now 1.1105. Look how close that is to my actual value, right? Compared to my first iteration, right? My first iteration for regular Eulers, that was my approximation. Now I'm 1.1105, which is very close to 1.1107. Let's come all the way back down here. Okay. So again, that was my approximation from just standard Eulers. And then using that with the improved Eulers, my y1 is actually 1.1105. Very close. A lot closer than I was with h equals 0.1. Okay. Remember, this had only 1 0 of accuracy. And here, these had, for most of these, only 1 0 of accuracy. Some of them, 2 zeros of accuracy. Okay. Here, I'm already 3 zeros of accuracy just on my first step using the improved Euler's method. Okay. Again. Okay. So I know the true value is 1.1107. So the first 3 digits are correct here. Versus me having a small step size, right? And doing this a whole lot of calculations, I have a semi-large step size and fairly accurate calculations, which is what I would have as a lazy person I am. Okay. So my next x is 0.1. My current y1 is 1.1105. So that's my next point. Okay, so I'm going to plug that back into my formula. Again, I'm not plugging that straight into y prime. I'm plugging that into y plus, it'll be my y2 star. So that'll be my current y value plus my step size times my f of x function, right? So y plus xy. So I have my current y value that I'm at plus my step size times my Euler's formula. So again, I'm using Euler's formula to find my approximate next value, right? And this approximate next value I would use to find my actual next value. So I have y plus h, y plus xy, right? Y plus xy. Again, don't let the 0.1 fool you, right? This is my actual x value. That's not my step size, right? That's from the current x value. So y plus xy. I plug all this into my calculator. As many digits of accuracy as possible. I got 1.232655. So that's my predictor, okay? So my next step that I'm going to use with my current step, right, is 0.2 for x and a y2 of 1.232655. Okay. So my actual y2, when I do this, I'm going to use my actual value. So to 1.1105, I'm going to add, right, 1/2 times h times my current value, x plus y, y plus xy, plus my next y plus xy, right? So again, this is coming from the current x and y. This second half is coming from the x2 and y star 2 being plugged into my equations, right? So when I plug all this into my calculator, this is my value that I get out, okay? 1.2455368. So that is my approximate value, right, for y2. So I'm not going to do this for every step, so let's look at a chart. Okay, so again here, notice that I'm cutting some values off, right? 1245538, and I'm just providing the first 4 digits, right? But I'm using lots of values, as you can see, for when I'm looking at my absolute and relative errors. Also, when I'm calculating these next values, I'm using as many values as I can so that this is as accurate as possible. So look how accurate I am with a step size of 0.1 and only having to do 5 calculations. Now, yeah, given that these 5 calculations I had to do were very long because each one required a lot of work, it's very, very accurate. It's more accurate than Euler's with 1. So look at my final percent that I'm accurate to, okay? The relative error here is very, very accurate, right? The absolute error between these two is very accurate, right? So the error appears in the thousandth place, right? So there's 2 digits of accuracy. If we go even to h, okay, for just a single Euler's, my final answer does not have 2 decimal places of accuracy. It has only 1, right? So this improved Euler's is much more accurate, obviously, than standard Euler's with a semi-large h, right? But even standard Euler with a smaller h, right? My improved Euler is more accurate than that, okay? With a fairly large step size, right? It's much more accurate. So then now let's look at what happens when we have h equals 0.05, okay? So we'll just go straight to the values. So here I have 3 decimal places of accuracy, right? Look at all these zeros, right? I'm very, very accurate, even from 0.01 to 0.1. So look, these are they're so accurate that I would have to show you more digits before you would see the error appear. Okay, same thing here. Okay, these are very accurate as well. Okay, very, very accurate values. 8675, 8682. Okay, so the error doesn't appear until the 3rd decimal place, right? Before the 3rd decimal place, actually, because of the rounding that's going on in my display here. So if we compare the global relative percent errors, right? So I'm looking at this percent error, okay? Even though I'm not taking it as a percent, I'm taking the exact value. If I want it as a percent, I would actually move 2 decimal places here, right? So I'm looking at this without making an actual percent. So this is just the decimal values, right? So this is from the h is 0.05. This is from h equals 0.1. Look at my difference in accuracy. It's a factor of 1/4. Okay, so a factor of 1/4. So for improved Euler's, reducing my step size in half makes me 75% more accurate. Okay, so stepping my step size in half makes me 75% more accurate. Okay, the local truncation error for improved Eulers is big O h cubed, and that means the local truncation is 0.h squared. So we saw that in the local truncation error of regular Eulers. So now we're getting this big O h squared truncation error globally for improved Eulers. So what that means is that improved Eulers is as good globally as Eulers is locally, so between each step. So this is much more improved, right? So by a factor of 2 basically, right? So as expected, halving the step size results in 75% less error in our final approximation. All right, so I will see you guys for the next video where we go over the Runge-Kutta methods, right? The standard sort of numerical methods we use for differential equations.